Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 8th, 2025, about a week ago. It shows that for most next word predictions in natural language, large language models only need a tiny slice of the recent text, with roughly 75 to 80% of long sequences being predictable from, at most, the last 32 to 96 tokens. The paper is titled Short Context Dominance: How Much Local Context Natural Language Actually Needs. And as we will see, the implications for long context reasoning and decoding strategies are quite significant. Alright, Figure 1 introduces the short context dominance idea using a story snippet about Sally, Carlos, and Gabby. The left side shows 3 growing context windows, where each window contains more of the original story, so the question at the end stays the same. The right side presents the model's next token distributions, which shift from wrong but plausible guesses to the correct word neighbor as more distant context is added. The key message is that only the third, slightly longer local window supplies enough information for accurate prediction. While Figure 2 turns the story example into hard statistics across models and datasets, the grids of histograms show how often a given minimum context length is needed before the model confidently predicts the next token. Most of the mass cluster is near the left, so short contexts dominate, with up to about 90% of cases solved by 64 or 96 tokens. The fitted red curves and negative slopes indicate a steep, power law-style drop in probability as the required context gets longer. Okay, Figure 3 extends this story by asking how distribution-aware minimum context length behaves under realistic sampling. The 4 panels show short and long documents under 2 Jensen-Shannon distance thresholds with different decoding methods in color. Most bars still pile up in the lowest context length bins, so short prefixes dominate even when sampling. Tightening the threshold from 0.2 to 0.1 spreads mass slightly, indicating that stricter similarity demands recognize more genuinely long context cases. Alright, Figure 6 turns that intuition into a concrete detector based on the long-short distribution shift score. The top Gov report panel shows short contexts clustered at very low scores, while long contexts pile up almost entirely above about 0.6. The bottom Reddit panel repeats the same pattern, which suggests this behavior is robust across very different datasets. Because of this clean separation, a single threshold around 0.6 already distinguishes long from short context cases with high reliability. So while Figure 6 showed how to detect long context cases, Figure 7 illustrates what to do once such a case is found. The left panel presents a story about Heidi, where the key to the blank is that she mainly spoke German. The central large language model box maps this context to 2 probability lists, one based only on the short local sentence and one using the full story. The right panels highlight that long context raises probabilities for German, French, and Italian, and a final boosted step further amplifies these long-range relevant options, so the next token distribution better reflects the full document. So, while Figure 7 illustrated how targeted boosting operates, Table 1 reports how much it helps on real question-answering datasets. The table compares vanilla decoding, context-aware decoding, and taboo across 4 models and 3 metrics for narrative QA, hotpot QA, and multi-field QA. Taboo consistently raises average F1 scores over vanilla and usually over context-aware decoding, especially for stronger models like QN27B, which shows the practical value of correcting short context bias. So while the previous figure focused on accuracy gains, Figure 32 addresses the cost of running the long-short distribution shift detector. The top panels show that detection time, which combines a long and short forward pass, grows with context length, but stays only slightly above normal inference for all 3 QN 2.5 model sizes. The bottom panels plot the extra cost as a ratio, and that ratio falls sharply as contexts get longer, dropping to well under 10% at 6,000 tokens. This pattern means the detector adds a small, predictable overhead that becomes less important exactly in the long context regimes where it matters most. So the big message is that most next word predictions really rely on a very short local window, while a small minority of cases need true long-range reasoning, which we can reliably detect and help with smarter decoding like Taboo. That has direct implications for scalable, efficient, long context systems. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.